Well, thank you all for coming. I guess you haven't gotten tired of me yet, but we'll see if anybody shows up next year. It's so nice to see so many great friends here tonight, and I think it should be a lot of fun. There's a lot of cool stuff that I want to try to show you tonight. So first I got to see if the technology is oh, you got this. As Pac said, the title is I got to learn how to zoom in here. Okay, here we go. Yeah, so pi and the whoops, wrong title. Sorry. Pi and the Art of Computer Programming. Okay, so the Art of Computer Programming is this book that I started to write in 1962, and by now, what I wanted to show you today was actually this. Zoom the other way. This is supposedly in bookstores maybe tomorrow. And I was hoping I would get my first copy today. This is not a real copy. This is what they call a galley. I think it's the only galley in existence. So this, at the moment, it's the only copy of Volume 4, Fascicle 5 that exists. But can you read it? It says Mathematical Preliminaries, Introduction to Backtracking and Dancing Links. Dancing Links is what I talked about a year ago. And so I'm going to show you a lot of goodies inside this book, and it makes a wonderful Christmas present. Now the story about Pi and the Art of Computer Programming, and it begins with a book that Martin Gardner published in the 60s, maybe about the same time as the Art of Computer Programming first came out. And it's called the Numerology of Dr Matrix. It collects a lot of columns that Martin described about his interviews with this remarkable I.J. Matrix, who is the world's greatest numerologist. And on page 60 of that book, we have this nice picture of pi here, where you see he gives the first 32 decimals of pi, and actually the 3 that come in front of those decimals. Well, I love this, and so I put it in the Art of Computer Programming in Volume 2. So Dr. Matrix has pointed out, for example, that the first repeated 2-digit number in the expansion of pi is 26. And its second appearance comes in the middle of a curious repetition pattern. There's 79 nested inside 32, inside 38. Okay, so there it is. And Dr. Matrix shows a lot of other things about pi. And then he says, pi, when correctly interpreted, conveys the entire history of the human race. Now that, I think that is, in a way you might say that the main purpose of my life then is to interpret the digits of pi correctly. What would be more important to accomplish it in a lifetime? Now a year ago I got the following Christmas present: pi to a million digits. This has been published actually for more than 20 years, but this is the 21st printing or something like this. So here's the first 10,000 digits, and then it goes on, and it has on the back cover you can see it's how to buy it. It's published by the Dark Side Communication Group, and they have. I mean, I had to have a friend help me with the Japanese. It says here, why in heck did you write this book? Answer: if you have to ask, you're not the right kind of person. Another thing in my files, somebody sent me this in 1981. This was the first time pi was calculated to 2 million decimal. that book, of course, but 1981 was not so long ago, and it was 2 million at that time, and it had, there were the person sent me the birthdays of the people who did the calculation. So a couple years went by, and it was 1983, and I got this, which is 10 million decimals of pi. So this is all on Microfiche. Now let's see if we can zoom in here. Yeah, we probably can't read it, but so here I have. Wow, okay, that's pretty good. So here I have 10 million. Okay, so the question is, of course, what's the current record? And the current record was set this year. We unzoom here. It was set on Pi Day. So 14th of March of 2019, the world record. Now the number of digits is 31,415,926,535,897 digits, and it was obtained using algorithms by Alexander E. I don't know, he might be here, and I think he lives around here, and Emma E. Wow, who led a team at Google, and I had the privilege of meeting Emma last month. So this is the current status of the digits of pi. Now, when I first began as an assistant professor at Caltech in the 60s, every once in a while they would have strange visitors drop in the department, and the secretaries used to send them over to my office, and one guy, a man came to ask if anybody had calculated the value of pi out to the end yet. 31 trillion, well, is that the end? Okay, so I tried to explain to him that pi was proved irrational, but that didn't seem to sink in. So I finally showed him a listing of, 100,000 decimals, and I told him that it hadn't ended yet. But I wish at that time I would have had tech done, because now I can show you pi all the way out to the end. That's all we need to know for that part. Okay, now, how do you remember all these digits? And well, I learned when I was young. See, now I have a rhyme assisting my feeble brain, its task sometime resisting. And so I count the number of letters. Now I have a rhyme assisting. So, and I learned that there's a better one. It's called, let's see, what is it? Yeah, I'm sorry. How I Need a Drink, alcoholic, of course, after the heavy lectures involving quantum mechanics. But anyway, you can count the letters. You just have to remember that phrase, and then you know what the digits of pi are, at least for a while. But I got to show you this incredible book, which is one of the greatest achievements of Ulipian literature. Not awake, 3141592655359. Sorry, 8. So a Dream Embodying Pi did this fully for 10,000 by Mike Keith. In the back, it's a play, a story, fantasies in modern verse and other writing, following without exception one of the textbook math motifs, pi's digits, and so on. This corresponding complete accuracy. This whole first paragraph is just perfect. But in the book, he does it for 10,000 digits. So here it is. So on the left, we see the first several hundred digits of pi, and Now I fall, a tired suburban in liquid under the tree. The idea is to make it seem as if he didn't have any constraint when he was writing. Now, of course, pi has zeros in it. And so what are you going to do with a word of length 0? No, so easy. Whenever he has a word of length 10, that means 0. And when he has a word of length 11, it means 1, 1. And 12 is 1, 2, and so on. So this is the language he calls Pi-lish. And he wrote this entire book in Pi-lish. So for example, you see the first 0 here comes at digit number 33, and that will be here, about bitterness of possible fortune. So the bitterness is 10 letters long. So there's the 5 and the 0. Then he's got double 1 here, and that's 11. So here, eyes of rationalism. You see, this is 4, 2, 1, 1. Okay. Now, looking a little further ahead, here's a case where he got 9, 9, 9, 9, 9, 9. You know, okay. So what does he do with that? Well, it was beautiful. Blameless, bloodless, guiltless, ceaseless, limitless, boundless. Okay. Real clear. So, now, so he, first he talks about things that he has little essays in here. He has short poems. He has, epigrams. And then, here's a dialogue between, taking two threads together. But, a movie. So here he's got, ZomPeer Chronicle. And it's a science fiction story. It makes sense, and the entire thing. Whenever Victor comes in, that means the digits is 6. Grigory comes in, it's 7, and so on. Voiceover is 9, and it all works. It makes sense. Actually. The real tour de force, however, is a crossword puzzle. Pi, a phrase, and all of the clues are actually no. This is the second crossword. The first crossword puzzle here. So narrow cattle path, is 6-0. Scandinavian is 1-2, and actually it's a real crossword puzzle. And it obeys all the rules of crossword puzzles for where the black squares should go in good thing. And the title is Reverend Spooner Upon Books. Well, it has this theme of Greaves of Lass. Here he's got Winnigan's Fake. I mean, these are Spoonerisms on books, okay? And then this all, another rule is that you ignore punctuation and numbers, so the numbers don't count. But then he talks about it, and he talks about the Spoonerism trio being a little difficult, and then he says, as I approach the doors, there's Will Shorts in an undershirt. I think Will Shorts is the great crossword puzzle editor at New York Times. I say ahem, detecting shorts missing. All right, so so there's more of this, and well, I've spent a lot of time on this, but he's also got a perfect sonnet in here. Let's see if I can find it. I think that was page 60. No, where is it? Okay. Yeah, here we go, page 78. 14 lines, exactly the right kind of masculine, feminine rhymes, and so on. So, Mike Keith's tribute to Pi. Now, this kind of served as an inspiration as I write The Art of Computer Programming, as you'll see. So now, pi, in the art of computer programming, of course, it occurs in its normal meaning as the ratio of a circumference to diameter of a circle. And for example, here's a part from the beginning of volume 1 where I'm talking about Stirling's approximation to factorials, and so here we have the fact that pi occurs in this rather weird way. That was one of my that was actually one of my computer music. That was in the year 2010. I gave my Christmas lecture was why pi. See, why does pi occur in the factorial? And it turned out there was a nice way to understand that. You can look it up online if you want. Okay, so now altogether, I counted today. I thought there would be more, but it turned out there were something like 1,700 places where pi where I could find the \pi followed by \b, which is a word break. I just used egrep, and I found about 1,700 places, which means pi occurs maybe once, twice every 5 pages in the book so far. Well, sometimes it only stands for permutation or something. It's not actually for the number pi, but most of those are for its real mathematical meaning. However, it often it is also used in order to show that whenever I need an example and pi is available, it shows that I didn't rig the example. So the first time I think I did this was in volume 1 on page 397. So it said what oriented tree on the vertices 1 to 10 has a canonical representation 3, 1, 4, 1, 5, 9, 2, 6, 5. Okay, so of course I didn't explain that this was pi, but the point was that that as I was writing this, I thought, I wanted the reader to try to do some examples, see if they could understand the rule in the text, and so nice choice for an exercise. And here's the answer to that exercise from the very first printing of the book, which was almost 52 years ago now. And so here's an oriented tree that corresponds to 3, 1, 4, 1, 5, 9, according to the rule that was described in that part of the book. All right. So, well, I have 2 comments here. One is, wow, those were the days when we had a lot of space for the illustrations. Right now, I wouldn't dare take up 3 inches of space for one illustration in the art of computer programming. What do you call it? The real estate. I have a very tight page budget, and I work sometimes 10 minutes to save a line. But the other thing that jumped out at me when I looked at this this morning was that there's a mistake here because I should have drawn I should have drawn arrows on it. It's supposed to be an oriented tree, so I was supposed to have arrows going up. And for example, on the next page, I have another, in the answer to another exercise, the exercise was about a different way to get a correspondence between digits and oriented trees. And in this case, had this picture. So somebody noticed that there were arrows on this side and not on this. So in the second edition that came out in 1973, this was finally corrected. Okay, now, where are we? I kept doing this over and over. Then when I had a good case, a good situation where I needed some number that was more or less random, I would use pi first. If I needed 2 such numbers, I would probably go to E or some other mathematical constant. But anyway, but the point being that since pi doesn't have any reason to be particular reason to be unusual, then my example is pretty typical of what you would find if you tried anything else that came across as something new that presented to you a new problem tomorrow. So that happened 18 times in volume 2, and it happened 5 times in volume 3, and it happened 30 times in volume 4A. Now, you can, how do I know this? Well, you can look in the index to the book. So if you look in the index of the book, you will see, well, I think I have a picture of it here. This is from volume 4A. So it'll say pi, as source of quote random unquote data, and then it gives these 30 references and says see also pi function. But okay, so then if you look at those pages, you'll see various ways that pi snuck in, and I want to show you now one of the more unusual ones in volume 4A. So this is on page 98. So near the beginning, when I needed a random boolean function of 4 variables, naturally you describe a boolean function of 4 variables by giving the truth table, which is a sequence of 16 zeros and 1. So I took the binary representation of pi, 1, 1, 0, 0, 1, 0, 0, 1. So, okay. In fact, I have a way to remember that. I can remember pi in octal the following. It's you start out with saying, you can say, most people only know pi in decimal. Now comes the phrase. But I know the octonal facts about pi. But I know the octonal facts about pi. But you say no very loud because it means 0. So 3, 1, 1, 0, 3, 5, 5, 2. And that's octal representation, base 8. And from that you can get the base 2 representation if you need it. Okay. Now, so here's a essentially random function of 4 variables, and so I the normal thing that people do with Boolean functions is to try to put them in 2-level form of as a OR of ands, and so here's the shortest way to represent that function: x1 bar and x2 bar and x3 bar or something. Okay, so it takes 10 steps to represent with 2-level logic this pi function. But on the other hand, on page 98, I'm talking about sneaky ways to calculate Boolean formulas that go beyond 2 levels of logic and allow you to use other gates. And so here it turns out that with only 4 gates, you can calculate this random function. And that's typical that most functions of 4 variables, there's some sneaky trick that human beings would probably not think of that actually does it. I can use the pi function again on page 205 when I'm talking about the representation of Boolean functions inside of a computer, because the best way to do that is a so-called BDD. One of these Christmas lectures in the past was maybe 2 of them were about BDDs. One of them was, I don't know, 10, 15 years ago. And so here, a more or less random function. Here's the way you represent it as in a BDD, which means if x1 is 0, you take the left branch. If x1 is plus, you take the right branch. And then you look at x2 and so on. And finally, you get to either false or true, and that tells you the value of the Boolean function. So this is one of the most important data structures. I got another use of pi here that probably nobody recognizes unless they go to the index, and it refers them to page 382, and then you have to figure out what on page 382 looks like pi. Well, I put it in yellow here so that you can see it's plus 0, 0, plus, plus, minus, plus, 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 minus. Anybody get that? So there's this one, maybe the most wonderful number system of all is the balanced ternary number system, which is base 3, and the digits are plus, 0, and minus. So here is pi in balanced ternary. You see, it means 1 times. I guess. Do I have a pen? Sorry. Here's a good pen. Yeah. Okay. So. Okay. So. The plus means it's also the same as saying 1, 0.011, and then minus 1, 1, 1, 1, minus 1, 0, 0, and so on, base 3. So this is 1 times 3 plus 0 over 3 plus 1 over 9 plus 1 over 9, 27 minus 1 over 81, and so on. You got the idea. So this is the balanced ternary, and so here was a case where I needed some string of plus zeros and minuses in order to describe an algorithm, and so what better than to use pi. Let's see, where am I now? This is C3. Good. So that's volume 4A, and as they say, there are lots of cases there. But now let's go to volume 4B, which is the part that that I'm currently working on it. And so volume 4B, I began writing the current volume in the middle. When you write a computer program, you do the initialization last. A few years ago, volume 4, fascicle 6 came out, and the section about satisfiability, and I gave some of my Christmas lectures about satisfiability during those years. And so this has, again, well, if you look in the index, we should be able to find pi. Yep. Pi as source of random data, 12, 14, so on, so on, so on. Okay. And the pi function occurs in this too. Okay. So that's fascicle 6. The middle part, the middle third of volume 4B. But the first third is what has now got me excited. This is the galley that I have here. A galley is the same as a real book, except for two things. The paper is thicker, and the binding falls apart rather easily. So I'm going to try to baby that. But if you open this book to a random page, like I guess I should turn to page 31 or so. Okay. So anyway, you'll probably find something about puzzles, because there are dozens and dozens and dozens of puzzles described of all different kinds. That I had a ball writing this, because it turns out that the kind of algorithms I'm describing here are best illustrated by their connection with puzzles. And the emphasis in the book is not on how to solve the puzzles, but how to create the puzzles. So I'll just scroll through a few more pages so you get a little of the flavor of of what's here. I'm in the middle of some exercises here. And I'll show you more details of some of these puzzles as we go. But anyway, this is the, and it also starts out with about 25 pages of it's called Mathematical Preliminaries Redux. This means I wrote the first mathematical preliminaries section in the 60s, and a lot of mathematics has been discovered since then. And so now I need to update that. But so it starts out talking about math. In fact, pi is used in a mathematical sense. Here, for example, in the Cauchy distribution and things like that. Okay, so now, but mostly puzzles. Puzzles galore, and puzzles of many different kinds. Each of these kinds of puzzles has its own little cult that has developed around it. So I know, so a lot of people have wasted countless hours working on this kind of stuff. But I like it because I know so many mathematicians and computer scientists who they chose their career essentially because they got hooked on puzzles when they were. Okay. Now, and of course, in the index of the book, it'll say pi as source of random data, and sure enough, there's plenty of there's plenty of these. So I'm going to show you most of the rest of the talk now. I'm going to show you about these. See, I guess I'll start with page. Yeah, 72. Okay. Here we go. These. Okay. All right. Well, what's one of right now probably the most famous puzzle of all time is the Sudoku, and and it turns out that this is the dancing links method that I talked about a year ago. It is the killer app for Sudoku. You present a Sudoku problem, and you use dancing links, and it just cruises to the solution. It's amazing. So I need an example of Sudoku to work on. Here it is. 314159265358979. Okay, so I was able to get the first 32 digits of pi in there. The other two examples, I didn't have time to work it out, but actually it's been proved that you need at least 17 clues in every Sudoku puzzle, and this one has only 17 clues. This one has only 16, so it doesn't have a unique solution. But this one, so the question is, I wanted to give an example with only 17 clues, but I had to deviate after a while. After the 9, 7, 8, then the last two are wrong. If somebody has time, I refer to, on the next page. The pi example that I gave, example A on the previous page, turned out to be a good way to illustrate the reason why dancing links work so fast on it. And so there's a chart here. But then afterwards it says now, of course, the puzzles aren't always this easy. This one has only 17 clues. That makes naked singles less likely, and so on. It comes from Gordon Royal's online collection of about 50,000 17-clue Sudokus. Now, nobody has compiled a complete catalog, but he's a really great graph theorist, and it appears to be nearly complete because for the last 10 years or so, nobody's been able to. Only rarely does anybody find one that's not equivalent to one of those on his list. So So if you have time, just go through and download these 50,000 and look at all the different permutations of them, and then look for a subset that goes 314159 to 17 digits. And then it also, of course, the 17, that has to be the 17 clues. So it's not, it's not out of the question that somebody would actually know whether or not there exists a better example that I could have used here. Okay. Now, by the way, when I had a lot of fun composing this example, and I thought it was an original idea. But I found out a couple years later that Johann de Ruyter had already put such a puzzle, a Sudoku, on his website, which had, I think, also 32 digits. I'm not sure. I don't remember how many. Johann, are you here? Yeah. Do you have 32 on the? Yeah. Okay. So it turned out then that maybe there, anyway, there's some muse out there calling people to create Sudoku puzzles that have clues with 314159, right? And then when I discovered Johann's website, I found that last year on Pi Day, he put this amazing puzzle online. Again, has the 32 digits of pi, and this is called a Japanese arrow puzzle, and so every box names the exact number of distinct digits that it points to. So, for example, 3 points down, so that means all these. What is it? 1, 2, 3, 4, 5, 6. This is 10 by 10. So of these 9 boxes, there's 3 distinct digits in there. Okay, so here's a 1. Of course, that's obvious, but here's a 1 pointing all the way down. So that means that all of the numbers in this column, except maybe the one at the top, are equal. So he's got all of the clues of pi, and it works out perfectly. I mean, there's a unique solution to this thing. So. Now I have an open problem in my book. Can you go to 33 digits of pi or 34? Now you have a little trouble because the 33rd digit is a 0. And that's why you can't do it in Sudoku. Sudoku, your cut 32 is the best you can ever get. But with this puzzle, you could have a 0 because you could have a box at the edge of the diagram that's pointing off. At the right-hand side, pointing to the right or something. It would be pointing to 0 different things, and so that would make perfect sense that you can have zeros. Maybe some of you will not get any sleep during the next month, but now in the published book this is rated 40, but I've changed it today to 41 because I figured it's a little harder than a 40 level exercise, and besides 41 is of course right there in pi. Here's a book that I found too. This is published in the Netherlands a couple of years ago. And look at the cover. Here's a Sudoku that has 314159 around a circle. They had to, in order to accomplish this, they had to add another constraint, and that is on each diagonal you need all the numbers 1 to 9. So this particular pattern, it has I don't know, 3,000 solutions if you only use the normal rules of Sudoku. But if you insist that this diagonal be 1 to 9, then it goes down to 8 solutions. And you insist that this diagonal also 1 to 9, then it's a unique solution. Okay, so a beautiful construction again. That same muse was over. Here's a proof that it can be done. Now, on page, okay, back to Classical 5. Now, let's go to page 76. Here we get to a very nice variant called, well, I like to call it jigsaw Sudoku. There has other names, geometric Sudoku, polyomino Sudoku, squealy Sudoku. But here's my example of a jigsaw Sudoku. So instead of you still have the rule that every row is supposed to have 1 to 9, every column 1 to 9, but then there's these regions, or the boxes aren't necessarily 3 by 3 boxes, but you have arbitrary shaped regions, and so it was possible to get a very nice puzzle, a jigsaw puzzle using the pi as the clues, and I was helped with by Bob Harris, who is the grandmaster of this kind of thing. In fact, he wrote, he found this example, which inspired the whole thing. It says Martin Gardner, and it's a jigsaw Sudoku, and it uses only the 9 letters, GRANDTIME, and of course has a unique solution. And when I saw that, I was inspired for my Christmas card 10 years ago was to make this, which the Christmas star rises, and again has a unique solution. Okay. So I try to give tools in the book that can be used as a help to this, but I don't think machine learning is going to be able to do this in the near future. So. On page 128, some of you might know that the New York Times, the Sudoku puzzles in the New York Times have an extra feature that they give you four extra 3 by 3 boxes, and and those are supposed to become perfect 1, 2, 3, 4, 5, 6, 7, 8, 9 as well, so it's called hyper Sudoku, and so here's an example. I think I was lucky that I could get hyper again. You don't need as many clues in hyper Sudoku, so but fortunately I could follow the digits of pi and make it. So the point is that we have a situation where there are zillions and zillions of sets of numbers that in this case satisfy the Sudoku constraints, the hyper Sudoku constraint, and so there's so many of them. You can expect that we can put extra constraints on. Okay. Don't just make a puzzle. Make a puzzle that does something extra, something unusual. And digits of pi is one of the natural, unusual things to strive for in cases like this. Okay. Now, the next one is even more fun. Knight and bishop Sudoku. So here, this was invented by David Nassin, who has a new book out on the subject, published by the AMS recently. So let's take a look at this diagram, for example. I want to zoom way in on this diagram. So, yeah, good. Okay, so here you see every row contains 3 knights. You have to look a little, but that's a chess knight. And every column contains 3 knights, and every little 3 by 3 box contains 3 knights. Okay, so this is 27 knights arranged on a 9 by 9 board, and in each one I wrote how many other knights are being attacked by it. Okay, so like this guy has a 3 in it. That's for 1, 2, 3. Okay, this has a 2. So it's this one and this one. Okay, there's a 0 here. This guy, okay, it didn't take, okay. So anyway, that's a configuration with 3 knights in every row column box, and I know how many are attacking. Okay, so now let's remove some of these clues and we just go to this. This is enough to reconstruct what was on the left. Okay, and what the clues are 3, 1, 4, 1, 5. Now a knight can only attack 8 other cells. So there's no way I could put a 9 in here. And if I had only 3, 1, 4, 1, 5, that wouldn't be enough clues to do it. So I just made 3, 3, 3. Okay, so there it is. That's 9, and that is knight Sudoku. Okay. Similarly, there's bishop Sudoku, and so here 3, 1, 4, 1, 5, 9, 2, 6, 5. This a bishop can attack 9 other bishops. Okay, so lots of fun there. Any questions on that?
What about 3 knights on the previous one?
What about what knights?
3 knights on the previous one. 3 knights in the lower. Could you please move the knights?
I forgot to wear my hearing aid. Can somebody else?
So go back, Don, go back to
Yeah.
that and look at those 3 3s there.
3 3s,
Yeah. Okay, 3 3s.
Yeah.
What about it? So each one has to be attacked by 3 others, and so if you go here, this one is attacked by this one, this one, this one.
How do they relate to pi number?
How do I relate to pi?
3 plus 3 plus 3 is 9, he said it.
Oh,
Go on, go forward.
That's it. 3 is a theme in this, and 9 is a theme in this puzzle. Okay. Well, there's a lot more than Sudoku, but I didn't really have a way to put pi into a lot of the puzzles that are related to things like polyominoes and stuff in here. However, here's one. In a jigsaw Sudoku, the regions have 9 cells, and so that's a polyomino with it's called a non-omino, and so if you study non-ominos, you can say that it's small if it fits into a compact square, and it's slim if it doesn't have any 2x2 any fat inside of it, and so there's an exercise that says how many non-ominoes are both small and slim, and then it says, oh, but now can you take 9 of those and put them into a 9x9 box so that we have a jigsaw Sudoku, and so then then the question is, okay, do that, and then design a puzzle that uses digits of pi, and here's the answer to that exercise, or one of the answers, because it says there are 16 solutions to part B, and so I solved. I did this for one of them, and I give the reader the fun of trying to do it on others. Okay. Now. Anybody here get the Guardian? Okay, so in Guardian doesn't have Sudoku. No, I guess it does have Sudoku, but it also has something called Furoshiki. And a Furoshiki puzzle is a 5x5 array where you're supposed to put in numbers 1 to 5. Each row and each column gets the numbers 1 to 5. But then it'll have every once in a while a less. You see, there's a less than sign here, so it says that whatever I put it here has to be less than that guy. Okay, and sometimes it'll less than sign is rotated. This turns out to be a kind of a pleasant pastime also, and it was carried over when the Guardian switched over to their new magazine format. So 31415, great. So so naturally, I want to give the reader a chance to exercise, have the fun of making up such puzzles. And so the exercise on the next page says, inspired by this previous one, construct a 9x9 Furoshiki whose diagonal contains 3, 1, 4, 1, 5, 9, 2, 6, 5 in that order. Every other clue should be a less than sign, not a greater than, not a vertical or horizontal version of it. And so that is, it turned out that was kind of a pleasant thing to discover. And if we zoom in on there, you see it's only less than signs occasionally. And of course, you try to have a few less than signs as needed to make the thing. So you start out with all 9x9 Latin squares that have the correct diagonal, and you try to narrow it down by until you get down to a unique solution. So that's Furoshiki. Another one based on Latin squares is called Ken. And here they have cages, regions called cages, in which you give a number and then you give a mathematical operation. So the operation is plus, minus, times, or divide. If it's plus, it means add together all the numbers. If it's times, multiply together. But if it's minus, it has to be only a size 2. And in the case of a minus, then you just take the difference of the two numbers. And similarly, with if it's a division, it has to be the region the cage has to be size 2, and you divide one number by the other. So here's an example where where you get a 2 after dividing one number by another, and if you're that's got to be either 2 over 1 or 4 over 2, because your numbers are only 1, 2, 3, 4, or 5. Okay, so this is Ken, and you see the clues here are 3, 14, 15. 9, 2, 6, 5, 3, it gets boring, right? So, but it's actually kind of fun to make up these examples, and so I asked, can you make a 9x9 Ken that has as many digits of pi as possible? And I had to finally leave pi after a while, but this is as far as I got. So I got 3, 1, 4, 1, 5, 9, 2, 6. So 5, 3, 5, 8, 9, 7, 9, 3, 2, 1, 3, 64. But then the last one I blew it. So by the time I had here, we still had more than one solution to the puzzle. And surprisingly, saying that the product of these 5 numbers is 3780 actually affects row 1 of the solution. It turned out, but I sweat blood over this one actually before. But maybe somebody can come up with a more perfect one. But there were times when I thought I would never make it. Now, that's Ken. Another one, of course, Sudoku got so popular, anything that had a Japanese name sort of became a bit of a craze too. So there's Kaku Roll, and actually the Kaku Roll puzzles have been around under other names, cross sums puzzle, since the 30s, Kaku Roll is where the different blocks. It's like a crossword puzzle, but instead of using letters, you use numbers, and then it tells you the sum of the numbers. But the rule is that the words in the solution they have to contain distinct digits. So in one row, you can use the same digit several times, but in one word, you can only use the digit once. Okay, so here was an example of Kokoro where the exercise is to use a computer to help you design a Kokoro that for which the answer, not the statement of the puzzle, but the answer to the puzzle is pi. So here's the solution to that puzzle. 31, 41, 59. Okay, so I prescribed the top row, and you're supposed to figure out some other clues for which force that to be the solution. Now, there are several other kind of puzzles too, not based on Latin squares, not based on this kind of digits, and one of the best is called Hidato. And that sounds Japanese too, but it actually comes from Israel. And so, but it's a completely different idea. Here we're given the numbers, and we're supposed to fill in so that we get the numbers, in this case 1 to 16, that form a path of a king on a chessboard. So a king covers all 16 squares, and it starts at 1. So it's going to have to go here for 2, and then 3, and 4 is going to have to be one of these 2s because it has to get to 5 here, and then somehow up to 14. And then 15 and 16, the way a king moves from square to square, diagonally or not, and so it's worked out the solution. Here's the answer. So exercise: can you make a hidatu that's 10 by 10 that uses the digits of pi as the clues? All right. Now. Let's take, so a 10 by 10 means that we have 1 and 2 digit numbers. And remember at the very beginning, I showed you how, if you looked at the digit of pi, there were these repeats. That there was this 26, 26 that came along. And so, as I was preparing this lecture, it occurred to me another puzzle I had never thought of before. How far can you go chopping pi up into 1 and 2 digit groups without making a repeat? So I don't want the 26. So I have to break this 26 up, but I can use 92 here. And so if I'm going to have a puzzle that uses distinct 1 and 2 digit clues, I wondered how far I could go, and the answer was that I could get up to 81 digits of pi. Before I was stuck, and there are 16 ways to do it. But anyway, this is one of the examples: 3, 14, 15, 92, and so on. But after this, I'm out of luck because I've already used the 9 somewhere up here, and the 8, 98. The 8 is already used, and so is 86 is over here somewhere. Yeah, 86. So I'm stuck at this point. But for this hidatu, you're going to have to find something. Well, it turned out that there is a way to get pretty far into pi. So 31, 41, and so on up to, I've got to 84 here, and. Turned out that this was probably the hardest one. Again, I thought it was going to be impossible, but then I showed it to my friend in Bulgaria, and he was able to solve it by hand. I don't know of anybody else who's able to do that, but it's really fiendishly difficult puzzle, but also satisfying to me that this was enough information to force the king path. That there's no other way to do. There's only one way to have the king is there after 31 steps, and it has to get over here by step 41, which means it has to waste time somehow. But there you are. Now to conclude, some of the besides these numerical kind of puzzles, Nicoli in Japan had come out with lots of really great puzzles that don't use numbers at all, but they only, but they like Masu, which only uses white dots and black dots as if you have stones on a Go board. And they also has one that uses numbers, but in a different way, and that's called Slitherlink. So a Slitherlink puzzle looks like this. You have a grid of dots here, and every once in a while you put in a number, and that number is the number of edges. The goal is to create a path around the dots, a single loop path, and if there's a 3 here, that path has to use 3 edges of the around that square. If it's a 2, it has to be 2 of the edges, and if it's if it's 0, it means it better not touch the square. So that's a Slitherlink puzzle, and I gave this. The convention is when you give the clues, it's nice to have them. If there's a clue in this corner, then you have a corresponding clue in this corner. So here's this example Slitherlink puzzle, and it says, what surprise is concealed in the following puzzle? And so you solve the puzzle, and here's the answer. Yeah, okay. You're just doing that because you want me to wrap it up. But as I say, Masu is another great thing which is based on stuff. So here, the question is now, find a way that each of these has to be either a white stone or a black stone. And the result should be a valid Masu puzzle that has only one solution. And that turned out to be a real fun thing too. So here's the book that I think is tons of fun, and it also, by the way, teaches a few algorithms on the side. Okay. Thanks a lot. Merry Christmas.